All right, then also welcome from my side. My name is Sebastian, and today I'm presenting DeepSTEP, which is short for Deep Learning-Based Spatial Temporal End-to-End Perception for Autonomous Vehicle, and today especially for Autoware. This work is a combination of a work from Florian, who just presented in the session before, and me, and we already presented a similar work back half a year ago at the Intelligent Vehicles conference. There we presented the first concept, and now we are working on integrating here everything into the Autoware universe code base. But first, let me get one step back to the motivation why we came up with this DeepSTEP approach for perception. Basically, what you can see now here is a short video sequence of our team. We participated in the Indy Autonomous Challenge in the last few races. This is a challenge where we race on different tracks all around the world with autonomous race cars. As you can see here in the middle, there are two cars. Basically, the blue car is our car, and then there's a green car which is trying to overtake us in a second. And you will see something that was not planned, but then I will explain what exactly happened.
150 mile per hour speed, polymove accelerating to the outside, 168 through the corners, nearly to 169. Now they crack 169, accelerating onto the front stretch in a spin from TUM down to the infield and able to continue on. No damage to the car, but what does that mean for TUM? I think that is day done.
Yeah, so what you saw here, like we were overtaken by the other car, and even though there was no collision from both cars, we still were spinning, made a very nice 360, but then ended up not finishing this race and ended up in the second place. So what exactly happened? Basically, this is how our perception pipeline looked like for the Indy Autonomous Challenge. And this is also how usually perception pipelines look like nowadays in autonomous vehicles. They are always based on this kind of modular approach, where on the left-hand side, you have sensor data as an input, which comes from multiple sensors, basically from LiDARs, from cameras, and from radars. But they are usually processed independently. And then we have two different pipelines. One is for detecting the objects, detecting the static and dynamically moving objects all around our car, our ego vehicle. This is based on some detection algorithms. And then basically, usually you have some kind of tracking where you kind of track those objects that you detected in the last time steps. You track them over the time of multiple time steps. And then in parallel, on the lower side, you see the localization. Basically, we need to know where our own ego vehicle is located at in the local reference. And at the end, the output of those two branches here is followed by the rest of the autonomous driving software stack, which is basically the prediction, the planning, and the control. So this is the modular approach. And what happened in our case here in the short video sequence that you just saw is basically that our detection, which consisted of a radar perception and a LiDAR perception, this radar pipeline detected a ghost object, so basically a false positive, which ultimately led to the tracking of this ghost object because we detected it in multiple time steps. Also, you can see here a short sequence what happened. Actually, the blue car is our car. We detected the orange bounding box. This is the other car. But as you can see here, we detect a lot of false positives. This is usually the case if you have some radar perception here. But then at one point we detect a lot of false positives, and the big problem is here the gray one, that we track this false positive objects because the pipelines are not communicating, the LiDAR pipeline and the radar pipeline. So yeah, let's wait until this video is finished. All right. And then at the end, what happened? Okay, we detected false positives, and then we replanned the trajectory. We made this kind of evasion maneuver and ended up braking and steering at the same time. High speed led to us leaving the track. Okay, so we have some key takeaways here. First of all, as soon as we have perception errors for example, false positives, they have a super high impact on the downstream software, because basically the downstream software, prediction, planning, control, everything relies on the perception output, right? So we need some kind of reliable software. The second key takeaway here is that the sensors in the usual pipeline, they are decoupled. So we have the LiDAR pipeline, we have the radar pipeline, but they are not kind of communicating. So if one of them has an error, this can also mean that even though the other one is perfect, we still have an error in the entire autonomous vehicle software pipeline. So we need some kind of intelligent deep sensor fusion. And the last key takeaway here is that, for example, in our case, we had this tracking algorithm which needed a lot of manual tuning. And as all of you know, manual tuning is basically you have a lot of parameters that you actually need to adjust, and at the end, this is something that is very error prone. So we were thinking, we need something that is learning based, so we can actually use the data to learn out of the data. And now let's firstly look briefly at the state of the art in AV perception. Basically, the task of object detection and localization are always decoupled. In terms of object detection, there's always the trade-off between if you should detect something in the three-dimensional space or if you want to detect it in two-dimensional bird's eye view space. Then there's the trade-off if you use only a single sensor modality, basically just using LiDAR or just using camera, or if you want to fuse them and use camera LiDAR fusion, camera radar fusion, whatsoever. In terms of localization, on the lower side here, it's basically always the point of if you want to use an HD map or if you want to go with the mapless approach. And as Florian already mentioned in the session before, this is always brings up the big question of scalability. Because if we want to drive here in Munich, yeah, of course we can generate a HD map, but then as soon as we drive to the next bigger city here, we need the same HD map, and this is just not scalable at some point. So there's kind of need for going to not using HD maps if we want to scale the AV stack. Probably a lot of you already know similar approaches in this area. This is just one example here. This is Bear Fusion. They're doing something very similar that we are also planning to do. Basically, they are using the input from several cameras, as you can see here on the left side, and then in the middle, they're also using the point cloud input. And at the end, they are outputting some detections, those bounding boxes here, but also the map semantics, as you can see on the right side, just information about the road, information about the lanes, and so on. That's quite similar, but then we saw that at the end we need to generate or to develop a kind of robust perception pipeline that is using multimodal sensor data, not only from LiDAR and camera as we saw before, but also using the radar, because it provides some very important information in terms of, for example, it's the only sensor that can detect or can directly measure the speed of the object it detects. So we want to integrate the radar as well. And then the very crucial point here is that we want to integrate the temporal domain. So basically, we do not only want to look at the current time step, what we can detect in the current time step and measure the current time step, but also want to take into account what we've already seen and extracted in the kind of previous 2, 3, 4, 5 time steps. So we want to integrate this temporal domain. Last but not least here, we want to enable some kind of information exchange between the task-specific modules, which means that the task for the detection, but also the task for localization, they kind of use the same sensor data, but also they extract similar information, right? So if you want to know where the lane markings are, for example, or want to know where the cars are, they are usually on the lanes. So it makes sense that those different modules kind of have some kind of information exchange and yeah, use the same data at the end. Now this brings me to our approach DeepSTEP, and you saw similar graphics before. On the left side we have the input from the sensors. In our case now it's the radar, camera, and LiDAR, and on the right side you have the output which goes to the rest of the pipeline, which stays as it is with the prediction, planning, and the control. And in the middle here, you have DeepSTEP. We will see this in detail in a second, where basically you have this spatial temporal deep fusion network, and then the task for detection and the local mapping, and they are fused in some kind of environment representation. Now let's have a deeper look into this pipeline in the middle that we just saw. As I mentioned, on the left side, we have the 3 inputs from the different sensors. Let's look into this. So point clouds from the radar and from the LiDAR on top, but also camera images from cameras, obviously. We extract some features to bring this into some kind of latent space, and this is actually the space that we can fuse in the next step here. And this is kind of the main framework here, where we fuse the latent space, but then also take into account the temporal aspect here, as I mentioned before. So we are planning to use transformers here, where we can basically include the information from the last time steps. Now we have some kind of shared latent space, which extracted all the relevant features, which then can use for the different perception heads. In our case, this is the detection and the local mapping to extract map information. They are fused, as you saw before, in some kind of environment representation. Now let's look into some potentials here. Of course, now with our approach with DeepSTEP, you do not have this high complex modules that you have the separate perception pipelines for the localization and for the detection, and then you need some additional tracking. Basically, everything here is combined into one module, so we have fewer modules, and this can be trained end-to-end. Second point here is that we are trying to leverage the temporal domain. As we saw, we have usually a lot of false positives if we do this without considering the last few time steps. But then if we leverage the temporal domain, this basically means that the network can learn that, for example, there was an object before and now it's occluded by another object, but then obviously this object cannot be gone. So this is something that the network can learn implicit. So it kind of gets scenario aware in this case. Last point here is that we want to conduct some kind of sensor and sensitivity analysis, because this is something I will show you on the next slide. Florian already introduced you to our new research vehicle, EDGAR. This is the car that we want to use to do some real-world studies with DeepSTEP. Currently, we are doing some kind of data generation. We collected the first data sets here in the city of Munich. We are currently labeling this data, and as soon as this is done, this process, we want to use DeepSTEP to, first of all, drive with this EDGAR vehicle here, which is completely based on Autoware, but then we want to replace the respective modules with DeepSTEP and check and do some kind of benchmarking how good our DeepSTEP performs compared to the current approaches. But then also, as I mentioned before, in terms of sensor sensitivity analysis, DeepSTEP enables, because it uses all the different sensors. As you can see on the right side, we have a lot of cameras, we have a lot of LiDARs and radars mounted to this car. We can try to use all of them, obviously, but then the goal would be to use as few as possible. And this is something that DeepSTEP enables, to actually check which sensors are really needed to drive autonomously. So as the time is running low, quick summary. DeepSTEP is a concept right now for spatial temporal deep fusion network. We are integrating this currently to apply this in the real world. And the main key takeaway here is that we are using multimodal sensor data, and it integrates a temporal domain. All right, that's it from Florian and me for today. And this was DeepSTEP. And now I'm curious if you have any questions. Thanks.